Good morning, everyone. Today we are going to see design of lexical analyzer generator in Unit 1, compiler design. So what is lexical analyzer? You already know it is a token generator, right? So how it is going to generate, how the design is looks like, we are going to see that. So main reason why lexical analysis is separate from the other phases, right? So the main advantage is simplifies its design of the compiler and it provides the efficiency implementation and it improves the portability of the compiler, right? So these are the three main reasons why we are separating our lexical analysis from the other phases. So this is our basic three phase connector here. Lexical analyzer on input is source program, that is group of characters, and it is generating the tokens to the parser. Then upon receiving the first token, it is asking for giving the message for get next token. Again, this process will continue until all the characters are read by the lexical analyzer. So these two phases are connected to the symbol table manager, that if there is any special symbol or any keywords or any special characters are stored in the symbol table manager. So if in lexical analyzer, if there are any errors, it will return to the error handler that there is an error message. So if any syntax errors, these parsers will generate the error message to the error handler. So we can see the one example how lexical analyzer generating the tokens. Suppose consider this equation y equal to 31 plus 28 star x. So we are giving the group of characters to the lexical analyzer, right? So it is generating what it is generating as a tokens. So see here, for each ID it is generating, it is one token for y, and assign these numbers 31 number. Now here id, the lexical analyzer is taking letters as identifiers and the numbers are taking num values. Okay, so here y and x are the identifiers and 31 28 are the numbers here. So these plus and star are the operators. Okay, so for each operator or for each identifier or for each number, this is going to create separate tokens for every character. So after this phase, it is going to input to the parser phase, right? So we have already seen in the previous session what are the tokens, patterns, and lexemes. Okay, so token means here, as we have discussed here, the numbers are created, numbers here, and the characters are created characters are created as identifiers, right? So here this is called as a token. A token is a classification of lexical units. So for example, identifiers and numbers. So lexemes means lexemes are the specific characters, that strings that make up a token. So lexemes means here special like ABC or 1, 2, 3. So group of characters. This is called lexemes. So what are the patterns here? Patterns are rules describing the set of lexemes. So these group can be called it as patterns. So that is letter forward by letter or letter followed by any letter or the digits. So regular definitions and the grammars. How we are going to design the lexical analyzer based on this grammar, right? So statement, suppose consider this statement, if expression then statement, or else if expression then statement, or else epsilon. So for this, for the regular expression will be if these are the special keywords which is stored in the symbol table manager. So for relational operator which we have in the source program, it is considered as a RELOP, that is relational operator. So LCs, these keywords are considered as same in the regular definitions. So here identifier means it may be a letter or it may be a digit. The number means all the digits. Number considered as all the digits. So these numbers and identifiers taken as term here, and these relational operators are taken as expression here. If there are any statements, we can take it as statement in the grammar. So consider we have constructed from regular expression to finite automata. But now we are constructing here for each relational operator, for identifiers and for numbers. Okay. So for relational operators, how we are going to construct finite automata, that is transition diagram. So take it from start symbol. If it is less than or equal to, it reaches the final state, which returns relational operator less than equal to here, right? So if there is equal to operator, then it is directly reaching final state that returns the relational operator, then equal, and then greater than or equal to. So greater than or equal to 7 here. So it is reaching final state that will return greater than GE, greater than all relational operator and GE. So if greater than any other symbols means if you get semicolon or colon, any numbers, so that will directly return relational operator greater than, not equal to. Here it is greater than equal to. If it is only greater than, then it is written GT here. So for identifiers means letter followed by letter, or it may be a digit. So first one should be a letter here. So here star means any number of times it can be repeated. So starting from the one symbol, that is letter. Okay. So it is reaching on letter other states. So any number of time it should be repeated. If maybe if it is another symbol, other symbol means if it is encountered any like suppose example greater than operator, anything if you get, then return get next token. Okay. So this, in this way the token is created. So we have a tools called lex and flex in the lexical analyzer. So what is lex? Lex is a program that is used to generate a lexical analyzer. So these translate regular definitions into C source code for efficient lexical analysis. And Lex and its newer function, that is flex or scanner generator. So the tools are called in lexical analyzer is Lex or flex. Systematically, it can be translated to regular definitions and it's into C source code for efficient scanning. It generated code is easy to integrate in C applications. So this is our design of our lexical analyzer. See here, when you are giving lexical program, you are saving with lex.l. So suppose your program.l means it is lex program. So .l program you are giving to the lex compiler. So for lexical analyzer also you have a compiler, that is lex compiler. So what it is generating? .c file, right? That is lex.yy.c. So initially in first lab what you have done, directly you have done C program and directly you are giving the C compiler .c program you are giving to the C compiler, and you are getting, after executing you are getting a.out file, right? But here in lexical analyzer we are giving .l file, that is lex.l file. When you are giving to the lex compiler, it is automatically generating, if there are no errors, directly it will generate .c file, that is lex.yy.c. This lex.yy.c input to the C compiler. Okay. So we are giving the input to the C compiler. So after compiling the C program, what you will get? A.out file. So for that A.out file, whatever you are giving the inputs, it will give the output based on your program. Okay. So this is our Lex specification, how we are going to write the Lex program in your lab. Okay. So LX specification consists of three parts. First one is regular definitions, and second one is transition rules, and third one is user defined auxiliary functions or auxiliary procedures. So we can see this in your lab program. Okay, we'll see one example. Here the transition rules are like actions like P1, P2 or any number of actions here. So regular expressions can be taken as match the character as X. These are all the regular expression which is used in LEX program. Okay. See here, what are all the characters we have used here? We are going to use in our LEX program. So initially you can start here is declaration. See, regular definition, that is declaration function. Okay. Declarations, all the declaration can be done here. These are the transition rules which we are going to execute, and these are the auxiliary functions which we are calling while executing, right? So these are the transition rules, and it we may contains the matching lexeme. So it should contain the matching lexeme, and YYLEX means here it will invoke the lexical analyzer program. So this is our second example. In this way also we can write our LEX program. First one is it is declaration. In the transition rules, we have regular definition called plus. Okay, for regular expression, we are giving the plus. So this is also same transition rules. Sorry, auxiliary functions. So this is another example how the regular definitions are used in the LEX program. This is always the same declarations, and this is the functions. These are changed according to your based on your requirement. So this is also another example. This we are going to execute in our lab programs. Okay. See here. First, what we are doing in yesterday's session, we have discussed how we are constructing DFA and NFA. How we are going to convert from NFA to DFA, NFA without epsilon moves. So from regular expression to NFA, then to DFA. So as we have discussed, NFA has a 5 tuple, that is start symbol, sigma, delta, and S0 and final set of finite states. Here S is a finite state and finite state of symbols, and it is mapping, which is a start state and final state. So transition graph also. Here we have seen many transition diagrams, transition tables. Okay, these are the examples. So 0 on A, 0 comma 1. 0 on A, it is 0 comma 1. This is nothing but NFA, because on 0 on A, it is moving 2 states. So this is all about how our design, how lexical analyzer is designed. Thank you for listening.